Here's how, right now, it's looking how the week is gonna play out. So today, first thing we're gonna do is we're gonna go in and finish up the lab from Friday, okay? You two are just gonna get started on the party. But you should be able to pretty much work quickly and kind of get done. If not, you might have to come in back before school tomorrow and finish it. So we'll go through that. We'll have kind of one big topic left, and that's molarity, which we'll kind of get through today, hopefully. And then that's Tuesday. We'll finish up kind of molarity tomorrow, and then kind of review Thursday. So it looks like this first big test over moles, dimensional analysis, doing conversion to density, all that stuff. It's looking like that's going to be on Friday. Okay, so if you want to plan ahead, that's kind of where we're at. So, as a teacher over the years, I just always assume, especially over a 3-day weekend, that you all have like offloaded a lot of information that we had before you all left on Friday. So let's just have a quick little jam session here, and go. Okay, so this is going to be one of the main central tenets that you have to get. So, like on that lab, for example, like let's say you want to figure out. Like on D, you want to have a certain number of atoms of aluminum, okay? So, first off, there's a couple of conceptual things that you need to remember. First off, atoms are incredibly small, okay? They are incredibly tiny. They're important, okay? If we didn't have atoms, we wouldn't be here having this discussion. So the cool thing about our universe and how it formed is that, number one, you have the capacity to have bonding. If atoms could never bond together, then we wouldn't be here having this discussion, because you wouldn't have DNA, you wouldn't have cells that make up your skin, you wouldn't have blood, you wouldn't have carbon dioxide, you wouldn't have an atmosphere, you wouldn't even have planets, okay? So because atoms can combine together, that allows us to exist, okay? We'll get into why that works later on. So, but those atoms are incredibly small. So that means if you have a small amount that you can see, within that, there's a huge amount of atoms within that, okay? So if you look like on D, where it says, hey, I'm going to give you a certain number of atoms, and I promise you, there are certain things I absolutely promise you. On this test on Friday, I promise you, I'm going to say, hey, 5.02 times 10 to the 24th atoms, okay? I'm going to say, hey, you need to measure out that number of atoms of, say, copper, okay? I'm going to say, how many grams are you going to measure? Now, if it would be handy if our scales measured in atoms, okay? It would be cool. So you could take your little weighing dish, and you could put that on the scale, hit the zero button, and then as you began to pour copper into that, it would read the number of atoms that you added, okay? It would be a cool deal, because you get these huge, massive numbers, okay? But here's the problem, is that we would have to have scales for atoms of copper. We'd have to have scales for atoms of aluminum. We'd have to have scales for water. We'd have to have scales for all these different substances that we have, okay? And it just isn't practical, okay, to develop scales for each possible element or compound that exists in the universe, okay? It doesn't work that way. Now you could make the same argument with moles. If I said, hey, Alec, I need 0.5 moles of sodium chloride salt. Okay, Mr. Burkham, he's going to go into the lab, he's going to grab a bottle of salt, and he's going to measure out 0.5 moles. And if the scale measured in moles, he could add that until the scale read 0.5. It reads 0.5, boom, here you go, Mr. Burkham, there you go. Okay, there, problem solved. But again, you would have to have a scale calibrated for every potential substance. for copper, for salt, for water, for potassium nitrate, whatever that is, okay? And it's just not practical. So the one common theme that unites particles and moles is mass. And so that's why we measure things in mass. And again, chemists decided, hey, we're going to take the relative atomic mass, and it's handy if you think about this in terms of a timeline. Remember, they knew relative atomic mass before they knew moles and before they knew Avogadro's number, okay? Because they had that. They had a chart. This is the periodic table. Oh, the relative atomic mass of carbon is 12. The relative atomic mass of hydrogen is 1. They had those numbers. So they said, well, what are we going to measure in? Rock, paper, scissors, boom, the grams guys won. They said, okay, we're going to take a relative atomic mass unit. I want to call that grams. They could have called it pounds, they could have called it ounces, they could have called it kilograms, okay? But chemists decided on grams. Physicists decided on kilograms, okay? So again, when I give this lecture in a physics class, a mole is a kilogram of particles, not a gram of particles, okay? So in physics, or the chemistry class, which we're in now, we said grams. Oh, okay, cool. So then they said, okay, that was the easy part. The easy part became, great, we measure out 12 grams of carbon, we're going to call that a mole. That was the easy part. The technically difficult part was counting the number of atoms in that, okay? That was the technically difficult part. How do you count particles that are that extremely small? Avogadro's hypothesis was that if you have a mole, okay, of any gas, he worked with the initial idea came with gases. He said, okay, if I have a mole of gas, which is 22.4 liters, which is about this much, okay, he says within this, it's all going to contain the same number of particles. Okay, great. Fill this up with hydrogen, carbon dioxide, helium, whatever gas that you want. Again, the challenge becomes, how do you count the number of particles that are in here? You can't see them. Okay? It isn't like, oh, I'll grab a helium. I'll just start counting atoms and pull them out. And then you can't do that. Okay, so that became the really technical, difficult part, was actually getting that number. Okay? So, once they established it, again, Avogadro, he said, hey, here's the idea. He didn't actually count the number. They did that later on. So here's the main idea. And again, I don't care how you think this through. If you like the math side of it, or if you like the visual side of it, and again, I promise you on the test, up there on that board, I'm going to have moles mole drawn out, okay? You don't have to memorize it. I'm going to have it drawn up there, and it's going to be up there on the board. So you got three things. You got mass, you got moles, and you got parts, okay? And if you go from mass to moles, what do you have to look at? Where's your source of information there?
Periodic table.
Periodic table. And if you're going from parts to moles, what's the number you're going to use?
Avogadro's number.
Avogadro's number, 6.02 times 10 to the 23rd. And here's what's most important. You cannot go from here to here. You cannot go from mass to parts. Okay? You have to go through moles. Okay? So it's a common mistake that's made. Are you ever going to say, oh, 1 mole contains 6.02 times 10 to the 23rd grams? No, why? It's about the mass of the moon. Okay? A little bit less than the mass of the moon. Okay? It's not going to happen. I'm not going to say, hey, yeah, I want you to get a weighing scale and measure out like a chunk of salt the size of the moon. Okay? It's not going to happen. So like on this one, so here's the deal. So like you got 5.02 times 10 to the 24th atoms of copper. Okay? And the sooner you embrace this concept, the better off you're going to be. You're going to go, oh, I'm going to put atoms of copper down here, and that's 1 mole, and that's Avogadro's number. So, Ethan, if I were to do this conversion, So take 5.02 times 10 to the 24th and divide that by 6.02 times 10 to the 23rd. Am I going to have more or less than 1 mole of copper?
You're gonna have less.
What's the bigger exponent, 10 to the 24th or 10 to the 23rd?
10 to 24.
Right. So if I take this 10 to the 24th and divide that by 10 to the 23rd, I'm going to have more than
1 mole.
1. So I know I'm going to have more than 1 mole because I have more than 6.02 times 10 to the 23rd atoms. Okay? Makes sense. So right away, I know I'm going to have, before I do any math at all, I'm going to have more than 1 mole. Okay? Got that. Now, Ella, do you have your periodic table out?
No,
Can you get that out?
yeah.
I need to know the mass of 1 mole of copper. Look in the middle of the periodic table, kind of off
63.5.
63.5 grams. Okay? So, now, because based upon what Ethan said, hey, I'm going to have more than a mole, that means when I get done with this conversion, I'm going to have more than 63.5 grams. So, again, before you do any math at all, step back and think, can I get a ballpark answer of what I should get? Okay? So, you do this. If you make these conversions work out, I can't guarantee you that you're going to work the problem right, but there's a really, really, really good chance. Okay? But if you don't do these steps, odds are it is not going to end well. Okay? So I beg of you, the sooner that you embrace this idea of doing these conversions, the better off you're going to be. You look at my answer keys. This is how I work them because it works. Okay? All right. So what you should have, did everybody kind of get through C-ish on the lab-ish? Okay. So you've got the aluminum, and then you're going to measure out the ammonium sulfate. Now, quick refresher. You're going to take that ammonium sulfate, and let's make sure everybody's cool with this. So this contains 2 common, what we call polyatomic ions that we're going to use. So there's 2 ways that you can do this. What I would recommend, again, on that sheet, okay, with your periodic table, ammonium is one that we're going to use a lot because it's a very common compound. So if you look at the molar mass of ammonium, you have 1 nitrogen and you have 4 hydrogens. So, Ella, what's the molar mass of nitrogen?
6.02.
No, the molar mass, the relative atomic mass.
Oh. 14.0.
14.0. And hydrogen is,
1.
but I'm going to have 4 of those, so there's 4. So that's going to be 18. So the relative, or the molar mass, the relative atomic mass of ammonium is 18. So up there, that's listed as one of those. So ammonium is going to be 18. That's one that we will use a lot. So what you can do is treat this as just like one thing. Oh, take 2 times 18, that becomes 36. Okay? So sometimes it just saves you some steps as opposed to going to counting. Oh, now what you could do if you don't like this, you can sit here and go, oh, I've got 2 nitrogens and I've got 8 hydrogens. Okay? Because what you're saying is that you have 2 of those groups. So you could either find the NH4 by itself and multiply that by 2, or say, oh, I've got 2 nitrogens and 8 hydrogens. It's a personal preference. Okay? It's however you want to solve this problem. And then you've got sulfate, 32.1 plus your oxygens. There you go. So you got that. So make sure, just want to make sure everybody's cool. How are you going to do that? So let's go over to the lab. Let's finish this up right quick. And then when kind of everybody gets that done, then we'll roll back into here and then we'll start talking about molarity. So, ready, break. All right. So here's kind of last really big thing that we covered, and this is this concept of molarity. So in terms of like a skill set that you have to really be a chemist, one of the things that you have to be able to do is prepare different solutions. Okay, so if you go like in the prep room, we have tubs and tubs and tubs of all these different solutions. And so I just went back and randomly grabbed 3 of them. So okay, so this is like a 0.20 molar solution of magnesium nitrate. Here's a 1.4 molar solution of potassium hydroxide. Here's a 0.5 molar solution of copper sulfate. So in the course of doing chemistry, you have to know basically what the concentration is. So the problem with so many solutions, if you look at a lot of the solutions, they all look like water. Okay? You can't tell by looking at it how concentrated it is. So, but if you take copper sulfate, for example, which is what I have here, and obviously if I dilute that, so in other words, if I take some of that copper sulfate and put that in here, and then I just add some water to it, you can clearly see that if you compare the two, okay, this is a lot more dilute than this is. So this is more concentrated, and you can just look at it and tell that. But the problem is that there's so many solutions, most of them, probably 90% of them, don't have a color to them. And you can't look and go, oh, well, if I take this 1.4 molar potassium hydroxide and dilute it, it's still going to look just like water. Okay, you can't look at it and tell, oh, it's more dilute. So what you have to be able to do is do that calculation. So there's 2 ways that basically this door swings. And those are the lecture notes that I printed out and gave to you. So there's 2 ways that this plays out. But it all hinges off one idea. And as complicated as molarity problems can be, if you keep one thing in mind, they're simple, okay? So any molarity calculation, doesn't make any difference. Any molarity. Doesn't matter if it's copper sulfate, potassium hydroxide, whatever it is. If you just remember that molarity stands for one thing, that's moles per liter. Okay, literally, if you keep this in mind, everything else becomes simple. So like this is a solution here that's 0.5 molar copper 2 sulfate. So what that means is that I have a half of mole in 1 liter. Okay? That's what that number means. Here I have, this is 0.2 molar. Oh, that means that if I have 1 liter of this stuff, I have 0.2 moles. There you go. So this is going to start off simple, okay? But if you just keep this in mind, molarity problems are pretty easy to work. So there's 2 ways that molarity problems play out. One is like a lab practical situation. I'm going to say, okay, hey, we need to mix up 500 milliliters of a 0.5 molar solution of copper 2 sulfate, okay? Because these solutions don't mix themselves. So when we mix these solutions up, the process starts by measuring out a certain mass of copper 2 sulfate, okay? That's what we have to measure out. We have to measure out that mass of copper 2 sulfate. And then we put it in the water. Because you start with the solid, measure that out, put it in with the water. Now, here's the problem. In case you haven't figured out, the scales don't measure in moles. What do the scales measure in? Grams. Okay? That's what they're going to measure in. So let's say, for example, and we're going to start off, let's say that I want to mix up 1 liter of 0.5 molar solution of copper sulfate. So this is my task. Like, let's say I know we're going to have a big lab coming up, and I'm going to mix, and I need to mix up a whole liter of this stuff. So what I have to figure out is how many grams of copper sulfate I'm going to measure into a dish that I'm going to add to 1 liter of water. so that I end up with a 0.5 molar solution of copper sulfate. So here's where this whole thing starts. So let's start with the idea that you're asked to prepare a 0.5 molar solution of copper sulfate. Okay? Now you also have to be told what volume that you're going to need. So in other words, I would say, hey, I need Emma to prepare 0.5 molar solution of copper sulfate, and initially I'm going to have her mix up 1 liter of this stuff. Okay? Cool, right? So, but the problem is, Emma goes in and she grabs the bottle of copper 2 sulfate, and it's a powder. Small problem. And the scale measures in grams. So what this means is that you have a 1/2 mole of copper sulfate per 1 liter. Okay? That's what that means. That's what that molarity means. If that was a 0.2 molar solution, I'd put 0.2/1. If it was a very concentrated solution, like a 6 molar solution, I would put 6/1. So the only thing that changes is the number that goes up there. Okay? Cool. Now, I got to get rid of the moles. So I'm going to put 1 mole down here. So if you follow this thought process, and if you make the units work out, life is going to be good. So the moles are going to cancel out. Now, 1 mole is equivalent to how much? That's what we have to figure out. So somebody take a calculator. So the molar mass of copper is what? You just had it on your paper. 63.5. What's the molar mass of copper?
Yeah, 63.5.
63.5? Okay. Sulfur's 32.1, oxygen is 64. So somebody takes 63.5 times 32.1 times plus 64. 159.6?
Yes.
Okay? Now, in this situation, I'm going to ask Emma to mix up an entire liter of this stuff. So at the end of the day, Emma just needs to know how many grams that she's going to need. She's got to figure out what mass of copper sulfate do I need to measure out. So because of the fact that she's going to mix up an entire liter, I'm going to multiply by 1 liter at the end. Because that's what she's asked to mix up, is 1 liter. So if you look at this, I'm going to take 0.5 times 159.6, and if you think about it, that gets me the mass of a 1/2 mole. Okay, that makes sense, right? That's the mass. Because if I wanted her to mix up a 1 liter, like a 1 molar solution, she'd measure out 159.6 grams. I don't need a 1 molar solution. I only need a 1/2 molar solution. So I'm going to take 0.5 times 159.6. Okay? That gets me a 1/2 mole. That's what I need. And I'm mixing up an entire liter of it, so that's how many grams I'm going to need. So somebody take 0.5 times 159.6.
79.8.
What'd you get?
79.8.
79.8. So here's how this answer is given. So it has a standard format. So Emma would say, Mr. Burkamp, I need to dissolve 79.8 grams of copper sulfate in 1 liter of water. Okay? That's what that means. Emma's basically going to give this answer by telling me this is what I'm going to do. I'm going to dissolve 79.8 grams in 1 liter, and you all can kind of visualize what 1 liter is, okay? About like this, okay? And that's what she's going to do. Now that's the simple one. But a lot of times, we don't need entire liters of stuff. We might only need like 250 milliliters of a solution. But it's the same idea, it just gets a little bit more complicated. So if I went to Emma and I said, hey, I need 250 milliliters of a 0.5 molar solution of copper sulfate. Now, it's a little bit more complicated, but not bad, okay? Now, here's what I want you to think through. If I need 79.8 grams to mix up 1 liter, which is 1,000 milliliters. Is the mass that I need to mix up 250 milliliters going to be bigger or smaller than, well, than 79.8? Smaller, why?
It's only 1/4 of it.
Yeah, I don't need a whole liter. I need 250 milliliters of this stuff, okay? So I know my answer is gonna be less than what I need to mix up an entire liter. I wanna show you 2 ways that you can work this problem, okay? You pick the one that makes the most sense to you, okay? The first one I'm gonna do is a continuation of this factor label method. That's the one that I would prefer that you do. So you're gonna start off the same way. They all start the same way. I need a 1/2 mole of copper sulfate in 1 liter, okay? This doesn't change. The only thing that changes is whatever this molarity is, okay? If this is 0.25, I'd put 0.25. If it was 0.1, I'd put 1. If it was 6, I'd put 6, okay? But it always means per 1 liter. In the next cell, you're always going to put 1 mole, and then you're going to put the molar mass up there, which we said was what, 159.6 grams of copper sulfate, okay? So you're always going to put 1 mole down here, and then the only thing that changes is the molar mass of whatever you're trying to find. Okay, if it was water, I'd put 18. If it was potassium nitrate, I'd put whatever that is, okay? Now, your last cell up here is you got to get rid of the liters. So what you need to do is take that 250 milliliters, okay, and go, wow, there's 1,000 milliliters in 1 liter, so that becomes 0.250 liters. So then your last cell out here, multiply by that volume. So now, look what happens. Your moles of copper sulfate cancel out. Your liters cancel out. You're left with nothing but grams. Okay, and that's all you need. Because Emma just needs to know how many grams of copper sulfate she's going to measure out. That's it. So, somebody take 0.5 times 159.6 times 0.25. Probably something around
19.
20. What'd you get?
19.95.
So 19 point. So here's how you would answer it. You would say measure, or you're going to add, let's do this. So you're going to add 19.95 grams of copper sulfate to 250 milliliters of water. Okay? There you go. So that's option number 1. Now, if you like ratios, here's how you can do this as a ratio. So, if you want to do this, okay, if you like ratios, here's another option. You just pick the method that works best for you. So at the end of the day, you have 0.5 moles per 1,000 milliliters. Okay, remember, 1,000 milliliters is the same as a liter. This means the same thing. So then what you can do is go, okay, I need 1/2 a mole per 1 liter is going to equal X number of moles per 250 milliliters. Okay, this is the same ratio. So 0.5 moles over 1,000 is going to equal X over 250. Okay, this is just the same ratio. Okay, so you can take somebody take 0.5 times 250 and then divide that by 1,000. Let me know what you get.
0.125.
0.125 moles of copper sulfate. So what that tells you is how many moles of copper sulfate that you're going to need. Now, obviously, again, the scales don't measure in moles. What do the scales measure in?
Grams.
Grams. So then you're going to go, oh, 1 mole is whatever that molar mass is, 159.6. 0.6 grams of copper sulfate. Then you're going to take 0.125 times 159.6, and then you're going to get that same answer. Okay? I don't care. I would prefer that you work it all as one big factor label method, okay, because it makes it easier. But if you're like, Burkamp, I think better in ratios, so some kids do, okay? But again, just keep this in mind. This means that if you start with that very idea that molarity means moles per liter, says, oh, that's 0.5 per 1,000 equals X over 250. This is how many moles I need. Boom, there you go. Okay? Got it? Good? Great. Now, here's the other way this door swings. How the door might swing also is that I might say, okay, hey, Ethan's going to dissolve 70 grams of salt in 400 milliliters of water. What's the molarity of the solution? Okay? So the other side of it is that you know how many grams you dissolve. So Ethan's going to go into the lab, and he's going to get a weighing dish, and he's going to measure out 70 grams of sodium chloride. Then he's going to dump that into 400 milliliters of water. And I want to know what the molarity of that solution is going to be. Okay, so this one, you know the mass, you're trying to find the molarity, right? So what's one thing you know you're going to have to do with those grams of sodium chloride? What do you have to convert it into? Ethan, what am I going to have to convert those grams of sodium chloride into?
H2O.
Nope. Let me give you a hint. It rhymes with oles.
Moles.
Moles. Because here's the deal. What molarity is a measure of what? Moles per liter. It isn't grams per liter. It's moles per liter. So I know I've got to convert the moles, or the grams, into moles. Old hat. At this point, you say, Burkamp, I can do that in my sleep. Okay. So here's the deal. You're going to start with the 70 grams of sodium chloride, right? So if you still have that lab, someone look up, find the molar mass of sodium chloride. $35.5. I know that's chlorine. What's sodium? 20. Is sodium 23?
23, yeah.
So 58.5. Okay? So here's the deal. If I stop right now, ramen, if this is all I do, what units am I going to have?
Grams.
Nope. Because my grams are going to cancel out. Well,
Oh, moles.
yeah. I'm going to have moles. Okay? So this is, if I do nothing else, if this is all I do, this is all I do, I know how many moles of sodium chloride I'm going to have. Ethan, is my answer going to be bigger or smaller than 1?
Bigger.
Why?
Because 70 is bigger than 58.
Fantastic. I know if I do nothing else, I know I'm going to have more than a mole of sodium chloride. Okay? Because my answer is bigger than, my mass is bigger than 58.5. Okay? Got that number. Cool. So here's the deal. So if you take 70 and divide that by 58.5, that's how many moles you're going to have. Now, what do you want your answer to be in? You want molarity, right? So here's your option. Your next option is you come out here and you take that 400 milliliters, okay? And if you can do this as a separate calculation, you know you got 1,000 milliliters, that's 1 liter. So that's 0.40 liters. So if you do this, okay, look what happens with the units. The grams cancel out, you get moles, and then you're dividing that by liters, you get molarity. Easy peasy, lemon squeezy, okay? So if you want to do this all in one step, that's how you're going to do it, okay? There you go. Now, if you go, Burkamp, I like to work this in steps. I think better in steps. Okay, fine. So somebody take 70 and divide that by 58.5.
1.2.
1 point what?
2.
1.2 exactly?
No. It's
1.2,
1.1965.
oh, so it rounds to 1.20.
Yes.
Okay. Moles, then what you can do, if you want to get that number by itself, and then divide that by 0.4 liters, do it that way, okay? Or you can just do it all in one step. It makes me no difference. But what you cannot do is just randomly write down numbers and expect me to follow what you're doing, okay? If literally all of these problems, if you start with the idea that molarity is moles per liter, they're not tough to do, okay? If you just start with that. Okay, so for your homework, you've got 9 molarity problems. Some of these are really, really simple. Some of them, not so much. Ooh, those are fancy nuts. Okay, so let's start off with a simple idea. So, number 1 is as simple as it gets. I gave you that in moles, and I gave you the volume in liters. So all you have to do on number 1 is take the moles and divide it by the liters. Cannot get simpler than that. 2 is a little bit more complicated because I gave you 480 cubic centimeters. But remember, how many cubic centimeters are there in a liter? How many cubic centimeters are there in a liter? 1,000. Okay? So you can take the 480. So if you're a little fuzzy, you might write up there at the top of this that 1,000 milliliters is 1,000 cubic centimeters, which is 1 liter. Okay? So that might be a handy dandy conversion to the numbers. So when you get to like number 5, I'm going to say describe the preparation of 1 liter of a 2 molar solution of potassium nitrate. So here's how I want this answer. So on number 5, you're going to give me a sentence. You're going to say, dissolve so many grams of potassium nitrate in enough water to make 1 liter of a solution. Same thing on number 7. You're going to say, dissolve X number of calcium chloride, grams of calcium chloride in enough water to make 25 milliliters. On 8 and 9, you're going to figure out what that molarity is. Now, when you get to number 9, okay, you got 65 milliliters of a 2.5 molar solution of copper 2 nitrate. How many moles of copper 2 nitrate are there in 65 milliliters? So, let me kind of show you what you're going to do on this one. And these are on your lecture notes. But here's the short version on number 9. So a lot of times what will happen is that you're given a volume like this, and you want to know how many moles I have in here, okay? Now the beauty of this is if you think this through, oh, I want an answer in moles. I got to get rid of the liters somehow. So what's going to happen on number 9 is that you've got 2.50 moles of copper 2 nitrate, which is CuNO3 2, okay? And that's in 1 liter. Again, start with the idea of what molarity means. This is how many moles you're going to have in 1 liter, right? Now, I don't have an entire liter of this stuff. I only have 65 milliliters of it. So if you want to, then what I would do, if you want to shortcut this a little bit, instead of 1,000 1 liter, you can put, oh, that's 1,000 milliliters. Okay, it means the same thing. So that's moles per 1,000 milliliters. It means the exact same thing. Then come in here and say, oh, I got 65 milliliters. So look what happens. The milliliters cancel out. You have moles. You multiply by the volume, you just get moles. So that's the easiest way to do number 9. So this is due on the morrow, okay? Now, if those lecture notes that are online, or that big packet that I've given you, there's also notes in there, okay? If you want to go through that, there's a video that shows you this. I'm also going to post this video online, so if you're watching this, you go, man, I forgot how to do this. Go to my YouTube channel, find this, you can watch today's lecture, okay? All right, ready, good, break? Got it. Okay, stop the camera, please.